To represent a number that's not an integer, the most common strategy is to use floating point numbers, as reflected by the float and double types in C. A floating point number is like scientific notation. It's some number times a power of 2, and it's a power of 2 instead of a power of 10, since we're working on digital machines. The float type in particular uses 32 bits total. It uses 1 bit for the sign, this plus or minus part, uses 23 bits for the m part, and it uses 8 bits for the plus or minus e part. Double is similar, 1 bit for the sign, but 52 bits for m and 11 bits for e. And the key to making floating point numbers work as nicely as they do on modern machines is the way that m and e are constrained and represented. Here in one slide is a summary of floating point representations using IEEE floating point values. We're going to again use 1 bit for the sign. We can generalize and say we're using k bits for plus or minus e. So that's 8 or 11 with float or doubles, but in general k could be anything. And we'll use n bits for m. That's 23 or 52 for float or double, but m again could be anything, and this encoding will work fine. The way the encoding works is that there are 4 cases. The first case is called normalize, and that's when the way we represent plus or minus e is not at its maximum or minimum value. Okay. So since we're using k bits, our representation of e we can think of as an unsigned number between 0 and 2 to the k minus 1. Right? So we call that number e. E is in that range. But the way we encode a plus or minus big E, right, that's our exponent here, is that we take the number that we want and we add 2 to the k minus 1 to it, and then we subtract 1 off of that, and that gives us a little e. Or going the other way around, if we've got the unsigned number in this blue region, we add 1 to it and then subtract off 2 to the k minus 1. So it's kind of like a 2's complement representation, but a little bit different, tweaked a little bit to work better for floating point numbers. Meanwhile, we represent the m part as a number between 1 and 2. So it can be exactly 1, but it can't be all the way up to 2. And the way we do that is we take the number that we wanted to represent. Right? M is going to be some fraction between 1 and 2. We subtract off the 1 part because that's always the same. Effectively, we save a bit. And then we multiply it by 2 to the n. So in other words, we shift it by n bits. Right? And then we get an unsigned. So flipping that around, if you've got the f, which is the unsigned interpretation of this green region, divide it by 2 to the n and add 1 to it to get the fractional number that corresponds to m. By constraining m to be between 1 and 2, then we make sure that each number we can represent has just one representation in that range. And what this normalized range represents is the big numbers all the way down to, but not quite 0. Right? Because we don't let e go to its minimum value, and because we constrain m to be greater than 1, we don't quite get to 0 here. Another property of normalized numbers is that they're more dense close to 0, even though they don't reach 0, and they get sparser as we go out. And that's just making good use of the bits to represent a wide range of numbers. But when we get close to 0, then we switch into denormalized form. And that's when the plus or minus e representation is at its minimum value. So there's a 0 there, which represents a negative e. It represents 2 to the k minus 1 negated plus 2. You might notice that this calculation corresponds to using 1 for e instead of using 0. Right? The reason that that off by 1 difference in encoding happens is because we constrain m to be between 0 and 1. So we're shifting m down by 1 bit, so that's why we move e's value up by 1 bit. Right? So here we encode m not by subtracting 1, we just multiply it by 2 to the n, or flipping things around, if you take the unsigned encoding, divide by 2 to the n. So depending on whether we've got a 0 in this first blue region or not, we treat the green region differently. This denormalized region, because e is at its minimum, we're getting around the origin here, and because m is allowed to be 0, we hit the origin. It turns out these numbers are uniformly spaced, right? Because e doesn't change, and m varies like integers, so it's uniform in the same way that integers are. And this turns out to be a good property for using floating point numbers, that we can represent a large range, but close to 0 we have a uniform coverage. There are 2 more cases. If e is at its maximum value, then and the m part is 0, then that represents an infinity, a kind of pseudo number that represents something smaller or larger than all the numbers that we otherwise represent. And the way this is used in floating point is when we might otherwise have overflow from adding things that are too big. In floating point, you don't get a wraparound effect or an unspecified effect. You get an infinity. Sometimes infinity is not right either, and then there's a representation called not a number. That's when the representation of e is at its maximum value, and the m part is anything that's not 0. So it turns out that there are very many representations that correspond to not a number.